The Earth revolves around the Sun and rotates around its own axis at the same time. In the revolution orbit, the winter solstice is on December 21st, where we have the shortest day and the longest night. The summer solstice is on June 21st, where we have the longest day and the shortest night. The spring and fall equinoxes are on March 21st and September 21st, respectively. On these 2 days, we have exactly 12 hours of daytime and 12 hours of nighttime. The revolution orbit forms an ecliptic plane, which is an oval shape, and the Sun is not at the center of the orbit. The Earth also rotates around its own axis, which is tilted from the normal of the ecliptic plane for 23.5 degrees. This is a plan view of the Earth revolution orbit, which is to view the system from the top. Now let's cut a section view through the 2 solstice positions and look downwards. So in the section view, the winter solstice will be on the left, summer solstice on the right. Note that the Earth rotation axis is tilted from the orbit normal by 23.5 degrees. We can rotate the Sun and the Earth on summer solstice as a system by 23.5 degrees clockwise, so that the Earth rotation axis is straight and the Sun is tilted for 23.5 degrees. A set of plan and elevation diagrams can then illustrate solar angles represented by needles at any location on any day. This example shows the summer solstice day. The needle diagrams on the following pages are recreated from Dr. Wayne Place's original needle diagrams. This is showing the Earth on summer solstice on June 21st, receiving a solar angle at noon. The upper image shows the polar view, which is to view the Earth from the top. The lower image shows the equatorial view, which is to view the Earth from the side. On this summer solstice day, the sun ray is tilted by 23.5 degrees. 30 minutes later, at 12:30 p.m., the Earth has rotated for 7.5 degrees counterclockwise, and it received from the Sun a new needle that represents the solar angle at 12:30. The old needle that was received at noon has been rotated for 7.5 degrees. Similarly, after 30 minutes, the point on the Earth receives a new needle at 1 p.m. At 7:30 p.m., we receive the last needle that barely arrives at the point. This represents sunset, and after that, the needles from the Sun will not reach the point due to the obstruction of the Earth itself. This is showing all 48 needles received on June 21st, each representing 30 minutes. The first needle is received at 4 a.m., indicating the approximate sunrise time. The last needle is received at 8 p.m., indicating the approximate sunset time. All needles received on June 21st form a cone-shaped cluster. On July 21st and May 21st, which are 1 month away from the summer solstice, the sunrise time becomes about 30 minutes later at 4:30 a.m., and the sunset time becomes about 30 minutes earlier at 7:30 p.m. Therefore, the daytime has become shorter than June 21st, but still more than 12 hours. In addition, the cone of the needle cluster is flatter than that of June 21st. On August and April 21st, the sun rises even later and the sun sets even earlier, and the cone shape is even flatter. On spring and fall equinoxes, which are on March and September 21st respectively, the sun rises at 6 a.m. and sets at 6 p.m., and there are exactly 12 hours of daytime and 12 hours of nighttime. On equinox days, the needles are in a flat plane, not forming a cone anymore. On February and October 21st, the needle cluster forms a cone again, but facing the opposite direction. The sun rises around 6:30 a.m. and sets around 5:30 p.m., making daytime less than 12 hours and nighttime more than 12 hours. On January and November 21st, the cone shape is more dramatic, and daytime is even shorter and nighttime is even longer. On winter solstice, December 21st, the sun rises around 7:30 a.m. and sets around 4:30 p.m. It has the shortest daytime and the longest nighttime in a year. The needle cone is in the same shape as on summer solstice, but facing the opposite direction. This is showing the needle clusters on the 21st of all month together. Now we can use these sets of needle clusters to study solar motion at different latitudes. Here at 45° north latitude, we only keep the needles on summer-winter solstice and equinox days for simplicity. We then add a ground plane. If we lay the ground plane flat, we can create a more realistic representation of solar motion. The needles above the ground plane represent the solar angles incident on the location of interest. Again, there are more than 12 hours of daytime and less than 12 hours of nighttime on June 21st. On equinox days, there are exactly 12 hours of daytime and 12 hours of nighttime. On winter solstice, December 21st, the daytime is shorter than nighttime. At 66.5° north latitude, the Arctic Circle, there is 24-hour daylight on the summer solstice, no daylight on winter solstice, and exactly 12 hours of daylight on equinox days. At the North Pole, the sun revolves for 24 hours at the same angle in the sky on June 21st. The sun skims the horizon for 24 hours on equinoxes, and afterwards it disappears for half a year. At the equator, the sun path is in the northern sky on June 21st, in the southern sky on December 21st, and straight above on equinox days. At the equator, there's a 12-hour daylight on any day of the year. Let's come back to 45° latitude and view the sun path in 3D with ground plane laid flat. Note the sun path on June 21st. The sun rises before 5 a.m. in the northeast direction and sets in the northwest direction after 7 p.m. On the sun path on March and September 21st, the sun rises at 6 a.m. in true east direction and sets at 6 p.m. in true west direction. On the sun path on December 21st, the sun rises around 7:30 a.m. in the southeast direction and sets around 4:30 p.m. in the southwest direction. Now let's isolate one solar position, such as 1 p.m. on equinox, and introduce two angles to define a solar position. The solar altitude angle is the angle between the sun ray and the horizontal ground plane. The solar azimuth is the angle between the projection of the sun's center on the ground plane and the due north direction. Now let's view the sun path system from the top in the plan view, with south pointing down. This is the basis of the Stereographic sun path diagram, a 2D graph to illustrate 3D sun paths. We can expand this plan into a stereographic sun path diagram, in this case at 50° north latitude. The highlighted lines are the date lines representing the sun path on the 21st of each month. The top curve shows the sun path on June 21st, the bottom one showing the path on December 21st. The middle curve shows the sun path on equinox days. The hours are represented by these highlighted lines that intersect the date lines. The intersection points between a date and the hour lines indicate the hours of that day. The solar altitude angles are represented by the concentric circular lines with designated degrees. The azimuth angles run around the edge of the diagram. The sun path diagrams can be used to find the solar azimuth and altitude angles at a given time for a given location. For example, what are the solar altitude and azimuth angles on March 21st at 4 p.m. at 50° north latitude. This is the sun path diagram at 50° north latitude. Here is the solution. Step 1. Locate the 4 p.m. hour line. Step 2. Locate the March 21st date line. Step 3. Locate the intersection between the hour and the date lines. Step 4. From the intersection, trace a concentric circle to the north axis to find the solar altitude angle, which is about 18 degrees here. Step 5. Through the intersection, draw a line from the center to the perimeter of the diagram and find the azimuth angle reading clockwise from the north, which is about 246 degrees here. Sun path diagrams can also inform designers of how the sun impacts a site and a building throughout the year. For example, use the sun path diagram to study how the existing buildings, building B and C in this design, impact the solar axis of the south elevation of the proposed building, building A. The buildings are modeled in Ecotect, and the sun path diagram is generated for the south elevation of building A. The diagram shows that the facade has no access to the northern half of the sky dome because it is facing south. Building B shades the south facade of building A from around 2 p.m. to sunset in the winter, and from 2 p.m. to around 5 p.m. during equinoxes. It does not shade the facade at all around June solstice. Building C shades the south facade of building A from sunrise to around 10 a.m. in the summer, to around 9 a.m. on equinoxes, and to around 8:30 a.m. in the winter. Solar motion must be considered to optimize solar gain in different seasons with different orientations. These graphs show the average solar radiation on a south elevation over time in Raleigh, North Carolina. The x-axis is the time of the day, and y-axis is the illuminance, which is an indicator of solar radiation level. The left graph shows the plots in June when solar angles are higher. The right graph shows the plots in December when the solar angles are lower. The data show that the solar radiation incident on south facades is lower in summer month than in winter month, which makes it a preferable orientation from the energy point of view. These plots show the solar radiation incident on east facade in June and December. The solar radiation is higher in the summer month than that in winter month. This can lead to overheating in the summer. West orientation has the same issue and can be even more problematic because the highest solar gain occurs in the afternoons when the air temperature is the highest as well. Both factors resulting in high cooling peak loads in the summer. Unobstructed upward-facing horizontal surface is the most problematic orientation in general. It receives extremely high solar radiation in the summer, resulting in a very high cooling load. This diagram summarizes solar radiation on various orientations as a function of the season. The x-axis is the month of the year, and the y-axis is the average daily solar radiation. Again, south orientation is optimum because it emits more radiation in the winter than in the summer. The solar radiation on north facades is low and does not fluctuate as much across different seasons. Therefore, north-south orientations are generally desirable in most climates. East, west, and upward-facing orientations have the issue of emitting more heat in the summer than in the winter. They should be avoided or be shaded as much as possible.